lesson in terms of our unit on limits. Obviously, we're going to do tons of practice problems with this. You guys have been reading the Calculus for Dummies, hopefully, and we're also going to do some activities in Desmos as well as on AP Classroom. So don't worry. Even though this is the last lesson, we're definitely many, many days away from taking the test on this. So let's jump into trying to figure out something about continuity. All right, so the first thing I want to talk about is the way that we figure out if a function is continuous at a point. So we're going to be looking at these three ways, these three conditions that we have to satisfy in order to say that a function is continuous at a single point A. If it doesn't hold true for all three of these, then we say that the function is discontinuous at that point A, or it fails to be continuous. Okay, so let's look at this first one here. All right, remember the first thing we always check is to see if it's defined at that point A. So if we want to see if it's continuous at x equals 2, we're going to plug in 2. So let's do f of 2. So that's 2 squared minus 4 over 2 minus 2. So that's going to be 4 minus 4, which is 0. 2 minus 2 is 0. So this is not defined. So f of 2 is not defined. So in terms of my conditions, right? Condition 1 says f of a is defined. This fails condition 1. So we are not continuous at 2. Okay? Let's go to the next one. This one says, determine whether the function is continuous at 3. So I'm going to plug in 3. In this case, it's piecewise. So when I plug in 3, I'm using the top piece, the opposite of 3 squared plus 4. So that's going to be negative 9, right? 3 squared is 9. The opposite of 9 is negative 9 plus 4, which is negative 5. Okay? Now, that satisfies the first condition. It exists. Or sorry, f of 3 is defined. But let's do condition 2, that the limit as x approaches 3 must exist. Now, we did this algebraically in a previous lesson, but when you look at doing the limit as x approaches 3 from the left, you're going to plug in to what we already did, right? The top piece. And when you look at the limit as x approaches 3 from the right, you're going to be plugging it into the second piece. So 4 times 3 minus 8. Now, when you do that, we already know this one gives you negative 5, and 4 times 3 is 12. 12 minus 8 is 4, right? Those must match if the limit is going to exist. So this limit, all right, as x approaches 3, does not exist. So it fails to be continuous at x equals 3 because it fails the second condition, all right? Let's do this next one. All right, determine whether the function is continuous at x equals 0. So let's plug in 0. It's another piecewise function. It says when x is 0, your y is 1. So that's a check. The limit as x approaches 0 must exist. Let's go from the left. All right, so that means from the left, we're doing, I guess we should do the first one, sine of x over x. All right, for any values that are not equal to 0. All right, and this is actually one that we talked about in the previous lesson. There was that hint that we had that said the sine of theta over theta, right, equals 1. All right, so let me show you on Desmos real quick. So that's the limit as theta approach 0, right, equals 1. So let me show you that on Desmos. So I'm going to graph the sine of x over x. Okay, and if I zoom in, you can see that as we approach this from the left and from the right, we're approaching 1, even though obviously it's undefined. Where is it? There it is. Even though it is undefined at 0, the limit is 1. So if both of these limits are equal to 1 from each side, right? The first one is 1, the second one is 1, then it does actually exist. So the limit as x approaches 0 from the left is 1. The limit as x approaches 0 from the right is also 1. So this does exist, right? It's 1. Now the last condition, right, is to say that the limit as x approaches a of f of x equals f of a. Okay? So when I look at this, what we're looking to see is f if these two match. So let me highlight them for I think that'll help. So does this number equal these numbers here? Okay, and it does. So this is continuous at x equals 0. So this function is continuous at x equals 0. All right, let's keep going. Now, this one is saying to find the values that for this function where it is continuous. Now, whenever you have a rational function, all right, the only issue you're looking for here is when you're looking at the vertical asymptotes, right? Rational functions, we have to be careful because we want to make sure we don't make our denominator equal to 0. So in this case, if I focus on the denominator, I know my vertical asymptote is x equals 5. All right, so this function is going to be continuous on its entire domain from negative infinity to 5 and then 5 to infinity. So it's going to be continuous from negative infinity to 5 and then 5 to infinity. So anytime you have a rational function, it's going to be continuous just except for the places where you have your vertical asymptote. Okay. Now, we want to actually classify those types of discontinuities. So in the first couple examples, all right, we found that we had a couple of functions that were discontinuous at a single point, and we can actually characterize them or classify them based on these three types: removable, jump, or infinite. Now, I will say this, that if you want ways to help you kind of remember them, all right, the thing that I think of when I think of removable is I think of looking for holes in the function. For jump discontinuity, a lot of times this happens with the piecewise functions. And then for infinite discontinuity, that's a lot of times has to do with your vertical asymptotes. Okay? So that's kind of the three ways that I try to remember this. So let's go back to an original problem that we did earlier that said this was discontinuous at x equals 2. Classify this discontinuity as removable, jump, or infinite. Now, if you use Desmos, you're going to have some issues with Desmos. I'll show you in a second. But the first thing I'm going to do is I'm going to factor the numerator. All right, it's the difference of two squares. And then you'll notice that I'm able to cross out x minus 2. So I'm left with just x plus 2. So if you graph this line, all right, that's all well and good. But because you crossed out this common factor, you have to have a hole at x equals positive 2. All right, and if you plug in that 2 into the what's left function, the x plus 2, so your hole is going to be at 2 comma 4. So when you graph it on Desmos, and this is kind of one of the issues with Desmos, if I graph the original, which was x squared minus 4 over x minus 2, all right, you have your line, but if you go to 2, 4, you'll think, oh, it's no problem, right? It's continuous. But as you move towards it, you'll see, there you go, that when you plug in 2 to this function, it is undefined. So that's kind of the issue that you have with Desmos. It doesn't actually show you the hole. So this has a hole. And so as I mentioned earlier, when I see the hole, I'm thinking this has removable excuse me discontinuity. Okay, let's go to the next one. Now this one we already showed was discontinuous at x equals 3, and I already mentioned that the key thing here is when I see a piecewise function and I see it's discontinuous at a certain value for x, that I know this is going to be jump discontinuity. So let me show you with Desmos why we say it has jump discontinuity. So we're going to type in this piecewise function. So we start with our brace, and we have the first interval, which is x is less than or equal to 3. And this is negative x squared plus 4, I believe. Let me confirm. Yep. And then x is greater than 3. And this one is 4x minus 8. Okay. I'm going to scroll so you can see it. Let me zoom out a little bit. So if you were to trace it from the left to the right, you're all good, right? No problems. But as we approach 3, right, we're approaching 3 from the left, or as we approach 3 from the left, we're approaching negative 5, which we already found. And then we have to jump up here, just pick it up at 3.01 and move that way. So because we had to jump to get to the other piece, that's why this is called jump discontinuity. Okay. This one here. Determine whether this is continuous at negative 1. Okay? If it's not, then classify it. So the moment I see this, I know it's a rational function. So I'm worried about a vertical asymptote at x equals negative 1. Okay? So I'm going to go into Desmos, plot it. And I kind of already mentioned this earlier in the lesson, but I kind of know what's going to happen here. I'm going to plot x plus 2 over x plus 1. X plus 2 over x plus 1. Okay, so I'm going to look at negative 1. And as I move to the left, or as I approach negative 1 from the left, I'm approaching negative infinity. As I approach negative 1 from the right, approaching positive infinity. So if you're ever approaching your infinities as you approach that number from the left and the right, you can see it's not continuous, all right, because we can't actually define it. It's undefined, so it fails the first condition. And the type of discontinuity is infinite discontinuity. All right.